Hello and welcome to Lecture 32 of Math 2R03. In today's lecture, what we're going to be doing is we're going to be looking at self-adjoint and normal operators. Now, just to kind of remind you about where we were, in the last lecture, in Lecture 31, we introduced what an adjoint is. And roughly, these are operators associated with transposes. So if you have a matrix, if you have an operator and you look at its associated matrix, MT, then you could take the transpose of that matrix and that corresponding operator is called the adjoint. That's a very rough way of defining what's happening. So in today's lecture, our goal is to introduce two special types of adjoints. Okay, so we'll be looking at kind of linear maps whose associated matrix comes from a transpose, but then there's some extra special properties that we're looking at. So we're going to be looking at what are called self-adjoint operators, and we'll be looking at what are called normal adjoints. Okay, so these are kind of our two special types of adjoints that we're going to be looking at today. Okay, I'll make myself disappear here, and we'll first talk about the first two parts of today's lecture are going to be on the self-adjoint operator. So an operator is self-adjoint if the operator T is equal to its adjoint. Okay, so what that means is that the inner product of TV with W is the same thing as V, the inner product of V and TW. Okay, and this is for all V and W in our vector space V. Okay, so this is kind of what we're looking at. We're looking at special linear operators so that when you do the inner product, you can either apply the inner product to the first entry or to the second entry, and you will get the same value. Okay, now at the matrix level, what this is saying is that the matrix of the adjoint, right, which we described last time, which is the conjugate transpose of the original of the matrix associated to the original map, is equal to the matrix that you started with. So if you're looking right here at this equality, and if we're looking at, say, the case over the real numbers, what this is saying is that if you take an n by n matrix, if A is the matrix associated to the transform, it has to satisfy that A is equal to its transpose. Okay, so another way of saying this is that A is a symmetric matrix. Okay, so when you see, the word self-adjoint being thrown around in today's lecture, you should think that kind of what we're trying to do is we're trying to generalize the property of symmetric matrices, provided all your entries were the real numbers. If you happen to be working over the complex numbers, what we require is that A is equal to its conjugate transpose. And the name for this, and you may or may not have seen this, is that we call this a Hermitian matrix. So a Hermitian matrix. So symmetric matrices, if all the entries are in R, are examples of Hermitian matrices, but the class of Hermitian matrices is actually larger because we're taking the complex and the conjugate transpose. But anyway, when we talk about self-adjoint operators, what we're talking about are those maps such that when you look at it at the matrix level, they're either the matrix or symmetric matrices if we're working over the reals, or they're Hermitian matrices if we're working over the complexes. Okay, so that's one thing. Now, one thing that's nice about self-adjoint operators is that every eigenvalue of these operators is a real number. Right, so there's no restriction on our vector space V here. It could be a real or it could be complex. But the point is, when we have a self-adjoint operator, you actually are forcing the eigenvalues to be real. And let me walk you through the proof here. So let's say that lambda is an eigenvalue with non-zero eigenvector V. Okay, so just remember what this means is that when we take t and evaluate it at V, it's the same thing as scaling our vector by lambda. Okay, so we have that information. But now let's look at, the norm of the vector multiplied by lambda. Okay, and what we want to say something about lambda. So lambda times the norm of v. Okay, so by definition, this is lambda times the inner product of v with itself. Okay, and we can bring in the lambda, because it's a constant, into the first spot. Okay, because it's an inner product. And now we use the fact that lambda v is equal to tv, so we can replace that by using the fact that it's an eigenvalue. And here is the part where we're going to use the self-adjoint property. Right? So here's the self-adjoint property, where this is the same thing as vtv. Then we use this fact to bring it back, bring back lambda back into the picture. So this is v lambda v. And remember, when we pull something out of the second spot, we have to take its conjugate transpose, right? So this is the conjugate, not the conjugate transpose, it's complex conjugate. We pull out the complex conjugate of lambda, and we're left with the inner product of v with itself. And sorry, this should have been a squared right there to make sure everything works out. And over here, then we're left with the conjugate, the conjugate of lambda times the norm of v squared. Okay, so now, because since this number here doesn't equal 0, right, because v is a non-zero vector, the only way that this can happen is if these numbers, lambda and its complex conjugate, are equal. But the only complex numbers that are equal to its complex conjugate are real numbers. Okay, so i.e. lambda is a real number. Okay. Now, if you've taken Math 2LA3, you may have seen actually this result proved in a special case. Okay, so you may have actually seen this result before, that if you have a real symmetric matrix, so a matrix A that you can think of this A is equal to its transpose, then every eigenvalue of A is real. So you know this even from Math 1B03, that when you take a matrix, even with real entries, you may end up with some complex eigenvalues. But if your matrix is a symmetric matrix, then you're always going to end up with real eigenvalues. And the reason that is because let T be the operator given by taking a vector x and mapping it to A times x. Okay, and then MT is equal to A, so the matrix of the adjoint is equal to the transpose of A, which is equal to A, which is equal to MT. So i.e. T star is equal to T, right? So the operator here is self-adjoint, right? So apply above result. So we know that this operator here has to have real eigenvalues. Actually, when we come back from the break, we'll take a pause here, I'll give you a different proof for this result, something that you would have seen in Math 2LA3. Maybe you did it or maybe you didn't, but I wanted to show you a different proof for this result. Okay, we'll pause here.